All right, closely related to the number of ways something can happen are what are called permutations and combinations. And this is 6.3 in Rosen's text. Now, first of all, you need to clearly understand what the difference is between a permutation and a combination. Permutations, as it says at the top of the slide, are ordered arrangements of a certain number of objects chosen from a given larger set. So there's an order to them, and that order matters. Like if I had 7 favorite books, I love these 7 books, but I can't display these books on a display at the underneath my TV or something. So I can only pick 3 of them. And then order matters. The first one, second one, third one. So I'm choosing out of my 7 favorite books, 3 books, and then arranging them in order of first, second, or third, where I wanted to make an arrangement. That would be a permutation. I'm choosing out of 7, I'm choosing 3 and arranging them in some order. In another case here, in this example on the slide, in how many ways can a teacher select 3 students to present their projects when the class has 25 students? Okay, so I'm choosing out of 25, I'm choosing 3, and the order matters. First, second, and third is specified there, so the order makes a difference. So there are 25 students to choose for the first position, for the first person to give their presentation. And then after that, there's 24 to choose for the second slot. And then there's 23 to choose for the third slot. So using the product rule, there must be 25 times 24 times 23, or a total of 13,800 different ways the teacher could choose 3 students to present their projects. Now, the number of permutations of R elements taken from a set of N elements is denoted by P of NR. So it's the number of permutations where you're taking out of a total of N objects, you're choosing R of them and then arranging them in some order. That's called permutations of N things taken R at a time. So in the next slide, we're going to look at how to calculate this quantity. So Theorem 1, using the product rule, says if N is a positive integer and R is an integer with R between 1 and N, so you're choosing out of N things, you're choosing somewhere between 1 and N of those things, then there are P of N comma R equals N times N minus 1 times N minus 2 all the way down to N minus R plus 1 different R permutations of a set with N distinct elements. Okay, now there's going to be a total of R numbers in this product here, but it starts with N and goes down to N minus R plus 1. All right. Now, another way to calculate it is using this corollary here. And it says if N and R are integers with R between 0 and N, so you could have R being 0, so you're taking 0 things. So there's only one way to do that. Anyway, so the permutations of N things taken R at a time, instead of using the formula we just had at the top of the screen, we could also use this. Now, N with an exclamation point, that means the factorial. Factorial means Okay, like 5 factorial would be 5 times 4 times 3 times 2 times 1 all the way down to 1. So it's the product of all the numbers from that number down to 1. That's what factorial means. And then you divide that by n minus r factorial. Okay? Now, we'll see that these are the same thing because this formula here is the same as the one at the top of the page that we just talked about, because n factorial means n times n minus 1 times n minus 2. In other words, all the way down to 1. But if we stopped at the point where we have n minus r and just put the factorial, which of course means continue all the way down to 1, and then on the bottom, according to the formula, we have n minus r factorial, these n minus r factorials cancel. You see that? They cancel. You got an n minus r factorial and an n minus r factorial on the top. And so those cancel, which really gives you the same thing as the original formula at the top of the page. So you can either use this formula at the top of the page, or you could use this formula with the fraction. Okay? And I'll show you that they both work. So here's an example. You want to choose 3 of your 10 most favorite books and arrange them in a prominent place on your shelf. How many different choices do you have, assuming the order of the 3 matters? Okay, order of the 3 matters. So that means it's a permutation where order matters. So you're arranging 3 things chosen from 10. So it's permutations of 10, 3. And so you could use the corollaries formula, 10 factorial over 10 minus 3 factorial. Now 10 factorial, that means 10 times 9 times 8 times 7 all the way down to 1. 10 minus 3 factorial, well, 10 minus 3 is 7. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, all of those expressions from 7 on down cancel. The 7 cancels, the 6 cancels, the 5 cancels, all the way down to the 1. And so really that leaves just 10 times 9 times 8. All right? Now we would have gotten this same thing of 10 times 9 times 8 if we had used the first formula, because 10 minus 3 plus 1 would be 7 plus 1, or 8. So it's 10 times 9 times 8, and we'd stop at 8. And so either way, you get 720 ways of choosing 3 books and then arranging those 3 books on a shelf out of 10 books. A coin being flipped 6 times. So I asked the questions, how many possible outcomes? Now in part A, it asks how many possible outcomes are there in total? Okay, so the solution, well, for each flip, there's 2 possible outcomes, and there's a total of 6 flips. So it's 2 times 2 times 2 times 2 times 2 times 2, or 2 to the 6th power, or 64 possible outcomes. All right, so when you flip a coin, 64 possible ways that can occur. All right. In letter B, it asks how many possible outcomes contain exactly 2 heads. All right. Now, one permutation or arrangement of the heads and the tails is HH and then TTTT. So that's putting the 2 heads right at the beginning. But of course, the heads could be anywhere in that list. Now, for the 2 heads, the first head could be placed in any one of the 6 positions, and then the second head could be placed in any one of the remaining positions. So now there's only 5 positions left to put it. So a total of 6 times 5, or 30 different arrangements of those 2 H's. But and you could use the formula and get p of 6 comma 2 and use the formula. You would get 30 also. Yet those two heads are indistinguishable. Now what do I mean by that are you couldn't tell if the first head was in the first position and the second head was in the fourth position, like this little example here. This is just an example. Suppose the first head was put in the first position and the second head was put in the fourth position. Well, that's the same as putting the second head in the first position and the fourth head, or I'm sorry, the first head in the fourth position. So these two arrangements are really the same because they're not different letters. They're the same letter, just you're putting them in two different possible places. And so we actually have to divide this result by 2 because we're counting twice as many. We're counting them as if they're distinguishable, that the two H's are distinguishable, but you can't tell the difference between the two H's. So we have to divide by 2. So, and then of course all the other positions you'd say are tails. So there's a total of 30 divided by 2, or 15 outcomes. Now, the question, how many possible outcomes contain at least 2 heads? Well, the best way to do this is to take the total possible outcomes, which is 64, and subtract the how many outcomes have either 0 or 1. See, we're doing how many have at least 2. At least 2 means 2 or higher. The opposite of that is 1 or 0. So if we can find how many have 1 or 0 and subtract that from the total possible outcomes, we could get the answer. Now, there's only one way to get 0 heads. You'd have to have all of them tails, and that's only one way to do that. But there are 6 possible ways to get 1 head. Well, it could be the first coin that's flipped, or it could be the second coin that's flipped, or the third coin that's flipped, or fourth, or fifth, or sixth coin that's flipped. So that head could be in any one of the 6 positions, okay? And so there's one way to get no heads and 6 ways to get 1 head. And so there's a total of 7 ways to get either 0 or 1 head. Now subtract that from the total possible ways, which are 64. So 64 minus 7 gives you 57 possible outcomes. All right, and then in the last example, how many outcomes contain the same number of heads and tails? Now, to have the same number of heads and tails, you have to have exactly 3 heads and exactly 3 tails, okay? So consider just the heads. We want the permutations of 6 things taken 3 at a time. So we calculate using our formula, p of 6 comma 3, and you can see my calculations there. B basically comes 6 times 5 times 4, which is 120. But those 3 heads are indistinguishable, as we talked about before, because where you place them doesn't really matter, whether it's the first head place or the second head place or the third place. So we have to divide by 3 factorial, which is how many ways there are to arrange 3 things. And so that's 3 factorial, which is 6. So if we divide 120 by 6, we get 20. Now the tails will just go in these other positions, so once we figure out the heads, we don't have to worry about the tails. So there, the answer then is 120 divided by 6, which is 20. So there's 20 ways to get 3 heads and 3 tails, or the same number of heads and tails. Now, combinations, though, the order does not matter, right? So a combination is simply a collection or a set of elements chosen from another set. Well, a set of elements chosen from another set is really a subset, and we'll talk about that later, but the order of the elements doesn't matter. So whenever you're choosing things and the order doesn't matter, then we're talking about a combination. So here's an example. Suppose a small business has 7 employees and 3 are to be chosen to work on a special project. In how many ways can this be done? Now, the order of the 3 employees chosen doesn't matter. You're just choosing 3 employees to work on some special project, and so this is a combination, right? Now, if order was important, then there would be 7 possible employees for this first position, 6 possible for the second position, and 5 for the third position, which is 7 times 6 times 5, or 210 different ways. But since we don't care about order or position, we divide this by the number of ways to arrange 3 things, which is that 3 factorial again. So we divide it by 6. So this example, we take 210 and divide by 6, and so there'd be 35 ways, because we're dividing by 6 because the order doesn't matter. Okay, now that's represented in a formula we're going to look at next, so we don't have to think about this, dividing thing. It'll automatically do that in the formula. So the theorem 2 says the number of R combinations, or combinations of taking R at a time. So we're choosing R things from N things, okay, where N is a non-negative integer and R is an integer between 0 and N, equals C of NR is N factorial over R factorial, and then N minus R factorial. Now, R factorial is this number of arrangements of R items that we've been dividing by, and so that's why it's kind of added to the denominator from the previous formula we had for permutations. So the difference between the formula for combinations and the formula for permutations is that you have this extra R factorial at the bottom, okay? But the permutations formula didn't have that. So so here's your formula for finding the combinations of R things, or I'm sorry, of N things, choosing from among N things, and you're picking R at a time. Okay, so instead of C and R, that formula here, we can denote the number of combinations of things taken, of R things taken N at a time, as this notation here, also with the big parentheses of N things taken R at a time. Now, corollary 2 says, let N and R be non-negative integers with R less than or equal to N, then C, or combinations of N things taken R at a time, equals the combinations of N things taken N minus R at a time. N minus R at a time. All right, we'll look at some examples that illustrate that. So look at this first example. How many ways can 2 team captains be chosen for a team of 9 players? So you got 9 players on the team. How many different ways are there to choose 2 people to be team captains, co-captains? Okay, well, you're out of 9, you're choosing 2, and the order doesn't matter. Okay, so that's why it's combinations. And so we go 9 factorial over 2 factorial, 9 minus 2 factorial. Now, 9 factorial means 9 times 8 times 7, all the way down to 1. But 7 factorial means 7 down to 1. So we could just write this as 9 times 8 times 7 factorial. On the bottom, we have 2 factorial, which is 2 times 1. And then 9 minus 2 is 7, so we have 7 factorial. Now, the reason I stopped at 7 factorial on the top is because I see that I've got 7 factorial on the bottom. And these two expressions, 7 factorial and 7 factorial, cancel. So we end up with 9 times 8 divided by 2, which is 72 divided by 2, which is 36. Okay, now here's another example. How many travel teams of 7 can be chosen from a team of 9? So instead of choosing 2 out of 9, we're choosing 7 out of 9 to form a travel team, okay? And so it's choosing out of 9 things, choosing 7 at a time. So it's 9 factorial over 7 factorial, and then 9 minus 7 factorial. But if you look at and compare this, we really have the same numbers on the bottom and the same numbers on the top. You have 9 factorial on the top in both cases. You have 2 factorial and 7 factorial on the bottom. Well, in this situation, you have 7 factorial and 2 factorial. So the 7 factorials again cancel, and you get 9 times 8 divided by 2. Okay? So this illustrates that theorem or corollary we just were talking about, because if n is 9 and r is 2, n minus r would be 7. And if you recall, this corollary said that C of nr is equal to C of n minus r. So that would be like the 9 minus 2, which is the same as 7. Okay, so we got the same result when we did 9, 2 and when we did 9, 7. And that'll be the case all the time, that you get the same result if your second number is n minus r compared to the first number, r. So why is it that there are the same number of ways of choosing 2 team captains as there are of choosing choosing travel teams of 7 players on each of those travel teams? Well, think about it. Choosing 2 captains is just choosing 2 out of the 9. And when you choose 7 out of the 9, you're always leaving 2 extras that will stay home and not travel. And so it's, and the same thing with the co-captains thing. Every time you choose 2 co-captains, you leave 7 that were not chosen. Now, I'm not trying to say that the co-captains will not be on the travel team, no, but it's just that it's the same idea. You're choosing, every time you choose 2, it's like choosing 7 on the other side. So it ends up to be the same number either way. All right, let's look at another example. How many different 5-card poker hands can be dealt using a standard 52-card deck? Okay. Now, when you are dealt a poker hand, does the order of the cards in your hand matter? No. The order doesn't matter. It just matters which cards you get. Okay? You can rearrange them in any order in your hand. That doesn't matter. What matters is the cards you get, not the order. All right? So this is combinations. And so we're choosing from 52 things, we're choosing 5 things. So this is combinations of, out of 52, we're choosing 5. So 52 factorial over 5 factorial times 52 minus 5 factorial. Now 52 minus 5 is 47. So on the bottom we have 47 factorial. Well, on the top, 52 factorial could be written as 52 times 51 times 50 times 49 times 48. And then the 47 factorial, I can just write 47 factorial and cancel that with the 47 factorial on the bottom. So then I can just multiply. Now, actually, all of the things on the bottom will cancel if you want to do this by hand and go the 5 will go into 50, the 4 will go into 48, the 3 will go into 51, the 2 will go into 50. So you can cancel everything on the bottom. It'll always be the case that your items on the bottom will cancel with something on top in these formulas, okay? But either way you do that, you end up with 2,598,960 possible poker hands. So there's like 2.5 million or almost 2.6 million different poker hands when you're dealt a 5-card poker hand when there's 52 cards. So I don't know if you expected that many, but that's the number there are. Now, permutations can have repetition situations too. Like, for example, in some cases, you could allow something to be repeated, used twice, okay? Some cases it's not. But let's look at permutations with repetition. How many strings of length R can be formed from the uppercase letters of the English alphabet? Now, strings means character strings, and it's okay to repeat a letter. You could have a string of A's, A. That would be a string. Or B, A. You could always repeat letters as much as you want. So there's no restrictions on repetition. So the rule, though, by the product rule, there's 26 choices for the first letter. There's 26 choices for the second letter, 26 choices for the third letter, etc. And you're forming a string of length R. Now, we don't know what R is, but R is the number of positions that we got to fill. So there's 26 times 26 times 26 times 26, all multiplied together, and there's R of them. So it's going to be 26 to the R power, okay? 26 to the R power, whatever R is. So if it's a string of length 10, then there's going to be 26 to the 10th power different strings that can be created with those letters of the alphabet, okay? Now, the Theorem 1 says the number of permutations of R objects from a set of N objects with repetition allowed is N to the R power. So N is how many objects you have to choose from. In this case, it was 26 because it was 26 letters of the alphabet. And then R is the number of things you're going to take and have in your subset. All right, or arrangement, I should say. This is permutations. Okay, example 2 on page 424. We're going to look at. So example 2 on page 424 of Rosen's text says, how many ways are there to select 4 pieces of fruit from a bowl that has apples, oranges, and pears? And it has as many as you want. It has at least 4 of each type of fruit. And it doesn't matter which apple or orange or pear you pick. It's just that you picked an apple, an orange, or a pear. Okay, so this one, it's probably the easiest way just to list all the possible combinations that you could do. Now, order doesn't matter, so it's combinations. So you could have 4 apples, or you could have 3 apples and an orange, or 3 apples and a pear, or 3 apples, I'm sorry, you could have 2 apples or whatever. So the solution here tries to list them in a systematic way. So you can see the columns that were done. 4 apples, 3 apples and an orange, or 3 oranges and a pear, or 2 apples and 2 oranges, or 2 apples, 1 orange and a pear. So you can see how they did it down the line. But as long as you just list all the possible ways, There's not really a formula way that really makes sense here, but there's a total of 15 ways. Okay. Now, example 3 is the next example. It's even more involved. And so I'm going to introduce a formula in Theorem 2 here. And this formula says there are n or combination. The formula uses this n plus r minus 1 comma r, or n plus r minus 1 comma n minus 1. So it's going to use the previous formula for combinations, but it's going to use this n plus r minus 1 as the n here. And this is used when you have when you're trying to find combinations of r elements taken from a set with n elements when repetition of elements is allowed. So this is what you use when repetition of elements is allowed and you're doing combinations. All right. So this is an example of that. Suppose there are 4 types of vehicles on display at an auto dealership: sedans, vans, SUVs, and trucks. Okay. Now, more recently, you can't tell the difference between vans and SUVs. Crossovers are kind of somewhere in between there. But let's assume that you can distinguish sedans, vans, SUVs, and trucks. The owner wants to display 9 vehicles, and he's going to choose from sedans or vans or SUVs and trucks. So how many different ways can he choose these types of vehicles, where the specific vehicle doesn't matter, but whether or not it's a sedan or a van or an SUV or a truck does matter? So one option could be choosing all 9 of them to be trucks, or all 9 of them to be sedans, or all 9 of them to be vans, or whatever. Or you could have 2 sedans and 4 vans and 2 SUVs and a truck. So there's a lot of different combinations, but the order you choose them doesn't matter. Just the type of vehicle matters. Okay. Now, in this problem here, n is going to be 4 and r is going to be 9. Okay. You're choosing from 4 categories and you're choosing 9 things. Okay. And so it says the number of ways to choose the 9 vehicles is the number of 9 item combinations. So you're doing a 9 item subset of a set with 4 elements when repetition is allowed. I could choose as many vans as I want of the 9. So using the theorem 2, there must be C of 4 plus 9 minus 1 comma 9. So that's using this first part of the formula. And so n is 4, r is 9, and then of course the r at the end is 9. So this, if you add that up and subtract the 1, you get 12. So it's really finding the combinations of 12 things taken 9 at a time. And if you apply the formulas we had in the previous slides, you get 220 different ways to display those 9 vehicles in terms of the types of the vehicles that you're displaying. Okay. Now that would be the same result if you did this, which would be 4 plus 9 minus 1, which is 12. And then 4 minus 1, which is 3. So 12 comma 3, that would also give you 220. And so that's another way to calculate it. Now, here's another example, example 5 on page 426. You can look at if you want, but the question asks, how many solutions does the equation x1 plus x2 plus x3 equals 11 have, where x1, x2, and x3 are non-negative integers? Now, non-negative means it could be 0 or it could be a positive number, okay? Now, if you're adding positive numbers and the sum of them is 11, then 11 is the highest that any of them can be, right? If one of them is 11, the other ones have to be 0, because you can't have any negatives, and it has to add up to 11. So 11 is the highest possible, all right? Now, this has a unique way of solving this problem. This is like asking how many positions can two separation bars be placed so that they separate 11 different ones. So I've listed 11 ones here. So that should be 11 if you count them. And then you're placing these bars, separation bars. You could place it here. Oops. You could place it somewhere in the middle. You could place it on the end, the very end, like this is, or wherever you want to place these two bars. Now, why are we placing these bars? Well, when you place the two bars, it separates into 3 numbers. So in the first grouping, to the left of the first bar, you see that this is the number 3. The ones in the middle is 8. There's 8 of those ones. And on the far right of the last bar is 0. So this represents the numbers 3, 8, and 0 to be your x1, x2, and x3. Okay? And so really, we've reduced this situation to where do you place 2 bars? Okay? Now you could place the 2 bars in between 2 ones where the 2 bars are right next to each other, and then you'd have, this number, 0, and then the last number to the right of it. You could place it anywhere, all right? So it really is reduced this problem into where would you place 2 bars. So thus, we are asking for the number of 2-element combinations of 13 positions. In other words, out of 13 positions, because there's 11 ones, and then we have 2 more positions of where we'd place those bars. So out of 13 positions, where would we place the 2 bars in that situation? And so this is out of 13, we're choosing 2. And so using the formula, you get 78. Okay. So that was a really unique solution. Way to solve this is think of it as placing 2 separation bars in among 11 numbers. And so it's a total of 13 possible positions. The bars could be 2 of the 13 positions, and the ones would be the other 11. But if you count up, including the bars, you have 13 things. So it's just where you place those bars is you're choosing 2 positions out of 13. Now, another way we could have done this, we could have used Theorem 2. In this situation, we're choosing 11 elements from or to go into 3 elements, okay, which are the variables, x1, x2, and x3. We're choosing 11 elements to go into 3 variables, and so it's kind of like the situation with the 9 displaying the vehicles, whether they're sedans or whatever. And so you have, you know, three elements where you could repeat where you place those ones. So it's like you're placing 11 things, but you're choosing 11 things, and you're choosing as many, you know, to go in the variables. So by theorem 2, you end up with 1311, which is the same as 13.2. So interesting how you can look at things differently in these problems. Now, try to find a place for myself here. These formulas for permutations or combinations, sometimes they don't allow repetition. You know, you can only choose one of each of the items from the set. Sometimes they allow repetition. When they don't allow repetition, then these are your formulas here: n factorial over n minus r factorial. And that could be written in a different way we had in the beginning. When it's a combination, well, you have to divide by the r factorial quantity on the bottom there. But when you're allowed to have repetition, then it's just n to the r power, okay? Because just like passwords, you're allowed to repeat letters in a password. And so if you have a 5-character password, let's say that we're talking about letters of the alphabet, you have 26 options for the first position, 26 for the second position, 26 for the third, 26, you know, so it's 26 to the 5th power. And so that's when you're allowed repetition. And then R combinations, when you're allowed repetition, this is like the SUV, vans, sedans, and truck situation. You're allowed to repeat those. And so the formula is n plus r minus 1 factorial over r factorial n minus 1 factorial, which is equivalent with what we already talked about. So there you have them all in one, but you have to distinguish which one to use and what the n and the r, you know, are referring to in each of the problems. So that's what the homework for, is to see if you can follow that. Now, one other case is permutations with indistinguishable objects. We've mentioned this before, how sometimes there are objects which are indistinguishable. So let me look at one more example to make sure you understand this. Let's say we have the letters Z-O-O. Now, if the O's are distinguishable, so in other words, we have an O1 and an O2, so you can distinguish which O you're talking about, okay? There are going to be 6 permutations of those letters: Z01O2 or Z02O1, and then O1Z02, O2Z01, and then O1O2Z and O2O1Z. So there are 6 possible permutations of those 3 letters. And that comes from 3 factorial, which is 6. But with ZOO, without using the subscripts on the O's, there's only 3 permutations. And here they are: ZOO, OZO, and OOZ. Okay, so you only have 3. Now, we had to divide by 2 factorial, because for each of those arrangements, like Z01O2 and Z02O1, now the O's are indistinguishable. So we had to divide by 2, so there, you know, is half as many possible arrangements when you can't distinguish between them. Okay, and I've mentioned here, these two Z0102 and Z0201 would be indistinguishable, as well as these others mentioned in the parentheses. Okay. Now, in general, the theorem then says the number of different permutations of n objects where there are n1 indistinguishable objects of type 1, n2 indistinguishable objects of type 2, etc. You might have a third indistinguishable object, whatever. The formula is n factorial divided by, notice we're dividing using that division rule, by each of the things that are indistinguishable. How many things are indistinguishable? Okay, so here's an example. How many distinguishable permutations can be formed from the letters in that great word Mississippi? Mississippi. Okay, so we know that there are 4 I's in that word, and each of those I's is indistinguishable. So you could say Ni is 4. There's also 4 S's, and those are indistinguishable. And there's 2 P's, and those are indistinguishable. So there's a total of 11 letters, but we have to divide by 4 factorial for the I's, another 4 factorial for the S's, and 2 factorial for the P's. Okay, and so it's not just 11 factorial, it's 11 factorial divided by those quantities. And so there comes out to be 34,650 possible arrangements or permutations of the letters in the word Mississippi. Okay, so you have to divide by how many are repeated, how many times they're repeated, how many letters, or the number of times that letters are repeated. So, I hope this helped you to understand these principles and how to apply them. It takes practice and takes some work, so work on it several hours to do the homework, and we'll see you, and have a good day.